we've got ground and ground. We've got a mass, or a little trolley of mass big M. We assume the wheels are frictionless and are small, so there's no inertia attached to that. The only inertia is to do with the mass, and that's got a spring K connecting it to ground. Okay, there's my first degree of freedom. My second degree of freedom is the fact that there's a pendulum attached to this mass. Okay, and to that pendulum is a force, horizontal force, F. Okay. Now I've set a couple of datums. I've said this is a datum in terms of the y, and this is a datum in terms of x. So y is upwards. This is minus y, which is y version minus yb. Okay, and xb is the horizontal displacement of Bob. This datum is the same as this datum. Okay, so obviously the distance is going to be x1 plus that distance there. Okay, so let's go through and sort this problem out. The first step is to calculate the kinetic and potential energies T and V. There's no damper in the system, so we don't need to worry about R. Take the coordinates of the Bob, okay, in terms of x and y. Well, in terms of x, I've got the distance x1 that the trolley has moved, plus L sine of theta 2, okay, which is my angle. Okay, if I go back here, you can see I've got x1, which is this distance here, and down here I've got the distance between this line and this line, which is going to be L, which is the length of the thing, times by theta, sine of theta 2. The y distance, okay, yb is going to be minus L times by cosine, which is this distance here, cosine of theta 2. So that's my x and y position. I then have to take the time derivative of those terms to get my velocities. We'll agree? Well, simply x1 becomes x1 dot. Okay, and taking the time derivative of this, well, this varies with time, so I have to take that out, take the time derivative, so I get L theta 2 theta 2 dot times by cosine of theta, because the derivative of sine becomes cosine. Here, the derivative of cosine becomes minus sine, so the minus disappears, and obviously, like I said, theta varies with time, so the theta dot comes out. Now we've got the velocities, we can determine the kinetic energy of the car and the pendulum bob. Remember, the energy, we're dealing with the energy of the system, not of the specific masses. Okay, so obviously with the system, I've got mv squared of the trolley plus mv squared of my mass at the bottom of the pendulum. Okay, so I've got mx1 dot squared. Okay, that's big M. That's the trolley, and then over here I've got x dot b of the bob and y dot b of the bob. Okay, with it times by the 1/2 of the small m. Okay, so I can go through. Obviously, 1/2 m features in both of these, so I've got these two things. I then substitute in my values for x dot b and y dot b. Okay, and I go through and I do a bit of multiplication out, and I end up getting this lot. Okay, so that if I do that, you end up getting this lot. Okay, and then obviously I can group them again. I get this sort of equation along here. Okay, just a bit of maths and algebra that you can go through yourself if you would like to do so. Fortunately, V is a little bit easier. There's no potential energy attached to the mass except for the spring, so we have to include that. Okay, and obviously mgh is the gravitational potential energy to do with the pendulum. Okay, which is what, as we saw before, minus mgl cosine of theta. Okay, we've got to work out the generalized forces first. In this case, we can observe that it's quite clear that if you've got a generalized force, the one appropriate to x is going to be a linear force. Okay, F is horizontal, therefore x will be pulled in a horizontal direction. And with the pendulum, if you've got a force at the bottom of the pendulum, that's generating a moment, and obviously the moment arm is F is horizontal, so the vertical distance, okay, which gives you the moment, is going to be L cosine theta 2. If I say Q1 is x1, Q2 is theta 2, which is perhaps why I gave this 1 and 2 subscripts. Big Q1 is going to be my force, okay, because that's this one, and big Q2 is going to be that moment that's being created by that force. So, L, T minus V, okay. Well, there's my T term, there's my V term, and then obviously I've just written it out in long form, taking out these brackets. So this becomes minus 1/2 kx1 plus mgl cosine of theta. So if we take the first I equals 1, so we're dealing with the x term, okay. If you look at L, the only term with x1 in, or x1 dot I mean, is going to be the first term and the second term in L. Okay? The third, fourth and fifth terms in L don't have x1 dot in it at all, so it's just those first two terms. Now the first one, we've got x1 dot squared, so they take the derivative, that becomes 2x1 dot, 2 times a half is 1, we end up with just m plus m times by x1 dot. The second term, we've just got x1 dot on its own, so you take the derivative of that, that just disappears, we end up with ml theta 2 dot times by cosine of theta 2. So that's the first line. Take the time derivative of that, well anything with a dot on becomes a double dot, okay? But because that second term, the ml theta 2 term, cosine of theta 2, both theta 2 both theta 2 and theta 2 dot terms vary with time, so you've got to use the product rule, which is why we end up with 3 terms for the next line down. Okay? We take the derivative of this with respect to time, I get ml theta 2 double dot times by cosine of theta 2, but this varies with time as well. So I have to take another theta 2 dot out, becomes ml theta 2 double dot, okay? And obviously the cosine turns into minus sine, so hence the minus there. Product rule. Now with L, if we look at the terms in terms of with respect to x1, well, there's only one x1 in L. It's the fourth term, 1/2 kx1 squared, and obviously the 2 comes down. 2 times a half is 1. We end up with k times by x1. But it's a minus sign because that's minus in L. Let's do number 2 as well. Okay, same process. So again, if I look at L, the only terms with theta 2 dot in it is the second term, the third term. Okay, so all the other terms disappear. So my second term becomes this. My third term becomes this. I take the time derivative of this. This becomes x1 double dot. Okay. This varies with time as well, so I get ml x1 dot times by theta 2 dot times by sine of theta, and then obviously this becomes theta double dot. Okay, which is where that comes from. And then obviously I take it with respect to theta. Well, that's only the second term and the fifth term in L. So the second term, this turns into minus sine, and this turns into minus sine, because they're both cosine in the equation. So if I group them together, for I equals 1, I get this as my equation of motion, which is not linear at all, okay? I've got 2 masses times by x1 double dot. Here I've got an x2 double dot, but it's multiplied by cosine of theta, so again, and here I've got an x2 dot squared times by sine of squared. They're not linear terms at all, okay? And for I equals 2, okay, you do the same thing. Again, set up with big Q, then you put the terms in, you end up getting those 2 terms. So again, I've just rearranged it, I've divided everything by L. I get my 2 equations there and there. Neither of those are linear. I can't write this in matrix form, but those are the equations of motion of the mass, x1, and the bob, theta. Okay. So that just shows you how you can find the non-linear equations of motion of the mass and the bob. And you cannot put them in matrix form, which would be something like that. Okay. You can't group the masses and the springs all together to give you this nice clean equation of motion. Okay.